Okay, very good morning to all of you and welcome to the first session of the second day of this non-Hermitian physics meeting at ICTS Bangalore. And today we have Naomichi Hatano with us uh, from the Institute of Industrial Science, Tokyo University, Tokyo. And he will be speaking on non-Hermitian Fabry-Perot resonances in PT-symmetric system. Naomichi, you can go ahead.
Thank you, Bhabani. Um, uh, Thank you for inviting me for this workshop. Um, it's a great pity we can't see face to face, of course, but it's also a great opportunity for to share our research with you. Okay, so my talk today is based on this paper. Okay. These two guys are students of this Dr. Imura, and I collaborated with basically with him. And here, the basically what we found. Let me summarize what we found first here. Oh, okay. Well, so I'm going to talk about the scattering problem PT symmetric systems. For PT symmetric systems, you typically have gain portion and loss portion, and it's connected by some kind of coupling. Um, but in our case, we particularly consider infinite scattering problem in infinite system. So this is scattering problem. You know, you learn this in elementary quantum mechanics. So we have incident wave here, and reflection wave here, and transmission wave here, and transmission probability is the square modulus of transmission amplitude. Transmission amplitude is the C over A here, while reflection amplitude here is B over A. Okay? Now, in a Hermitian problem, this T and T plus R is always 1. But in non-Hermitian problem, because some portion of fluxes comes into the system from the gain, and it's absorbed at the loss site. So this T and R, T plus R typically is not equal to unity, and otherwise we found this very interesting features. So gain and loss potential is sort of a non-Hermitian potential. When this non-Hermitian potential is weak, we saw some kind of very anomalous resonance peaks, while when it's strong, uh, I mean, when non-Hermiticity is strong, then we found rather classic Fabry-Perot resonances. And I'm going to tell you these two features in this talk. Okay. Now, let me remind you the PT symmetric system. I do this because to remind you the matrix representation of the PT symmetric system. So, for example, suppose you have at site 1, you have a gain plus I gamma potential. And at site 2, you have a loss potential, which is represented by minus I gamma. And they are connected by the coupling TH. Then T hopping, actually. So then Hamiltonian is given by this matrix. Okay, this is the I gamma is this potential. Potential is given in this representation. Potential is given on a diagonal elements. So the potential at site 1 is here. Potential at site 2 is here. And here is off diagonal elements that couples site 1 and site 2. Okay, are you okay with this matrix representation? Then we let me move on to the scattering problem of the infinite system. Okay, so we consider that we will, our main problem here is this scattering problem. So here is the gain potential, and here is the loss potential, and there are here, if you name it 0, then we defined that the loss potential is distance L away from the gain potential. Okay, then we consider the incident wave A, reflection wave B, and transmission wave C. Okay, and this is actually a tight binding model. So particles only can hop from side to side like this. Okay, just like before. Okay, so the particle can hop from here to here, here to here, just like this. A particle can hop from here, here, blah, 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 here, and here, and here, like this. Okay, so this is a tight binding model, which is quite familiar to condensed matter physicists, but I noticed that many are not familiar with this tight binding model. So let me a little bit talk about this. So it represents a lattice structure of in a solid system, but you can also see this as a discretized Schrödinger equation. Okay, um, and I'm going to talk about actually the continuum Schrödinger equation later on, if I still have time. Okay, so this system can be represented by this three-diagonal matrix, Hamiltonian matrix. So here is the diagonal gain potential. Here is the loss potential. I wrote only 2 zeros here, but there must be L minus 1 zeros here, pieces of zeros here. Okay, and this continues all up to infinity and all down to infinity. Okay, so that's the Hamiltonian matrix. So it's an infinite times infinite matrix. Okay, so and we try to find the transmission amplitude for this Hamiltonian matrix. But let me start from the one-side complex potential. Okay, so it's a tutorial example, but actually we are going to use this later in the PT-symmetric system later on. Okay, so in this case, the Hamiltonian has only a diagonal element at 0 plus I gamma, and hopping all along. Okay, so in the previous Hamiltonian, we now in this tutorial example, we don't have this lossy potential. We have only this gain potential, but otherwise it's the same. Okay, that's this Hamiltonian. Okay, then we want to let me solve this problem, the scattering problem of this for you step by step, because I still have time. So so this is the Hamiltonian, and first we consider this area or this area. Okay, let me first consider this area. So this is the wave function that we assume, and in this area, this assumed wave function has this form. Okay, it goes to the right. Okay, that's this assumed Hamiltonian, and we try to find the eigenvalue for this Hamiltonian. Okay, so to find the eigenvalue, we operate this Hamiltonian to this as an ansatz, and we try to find this element at x greater than 1. So on the right side. Okay. Then when this element applies to this, then only the element and only the element at when x equal y survives. Okay, so we have this kind of portion. Okay, for out of this. Okay, on the other hand, if this element operator applies to this, then x plus 1 must be equal to y. Okay, so this which means that x must be y minus 1. Okay, so in this sense, this operator times this so has only this portion. Okay, but because for x greater than 1, we have only this element, so x plus 1 psi means x plus 1 x times psi times this element. Okay, x minus 1 psi can be written in x psi times e to the minus ik. Okay, so then actually from this we found that this is actually the eigenvalue, right? So eigenvalue is actually written in this way, and if you consider th to be minus and k around 0, then actually it's like this around 0, and this is actually a discretized potential version of the harmonic oscillator, oscillator. Okay. Now this is the eigenvalue of this. So what we do next is to solve the Schrödinger equation for x equals 0. For x equals 0, this portion gives this portion gives this, but for x equals 0, we always also has this potential. So the potential terms looks like this. Now, this one, similarly to this, this portion gives you C, IK, while this portion, because this portion is on the negative side, so this portion gives you A e to the minus IK plus B e to the IK. Oh, sorry, this must be on the shoulder. Okay. Now this is eigenmass C, and if we if and this must have the equal to this eigenvalue problem. So this equals to this gives you one equation for A, B, and C. Okay. Now and we also have this equation because because we have this situation. So A plus B must be C at here. Okay. So we have two equations for A, B, and C, right? One equation, this equals to this, and the second equation, this equals to this. So we can find the ratio between C and A and B and A, and they give you the transmission amplitude and reflection amplitude. Okay, this is how we find we solve this problem. Yeah.
Yeah, this your second equation A plus B going to C is not supposed to be B plus C equal to A, because reflection plus transmission should be incident, right?
No. That's that's the
your A
that's no wave function. This is not the probability. So wave function on this side has this this plus this. Okay. And wave function on this side must be this here, and the wave function must be a continuous.
Yeah, I got it. Yeah.
Okay. So it's really like what you learn in elementary quantum mechanics. You have a potential. Then here the potential, the wave function must be continuous, and the first derivative of the wave function also must be continuous here. Okay, so that gives you the two equations, right? And actually, so in this discretized version, this is the condition for the wave function continuous. Actually, this equation is equivalent to the um, to saying that the first derivative of the wave function is continuous. So these two equations appear out of because of this continuum conditions. Okay. Now, so by solving these two equations, we can find the T and R. And in this particular one-side problem, we find this. Okay. So this is the transmission amplitude. If you square modulus, uh, the square modulus of this is the transmission probability. Okay. Now, this you find that this diverges at k, at the real k, this value, and for this to be real, we must have this weak non-hermicity condition. Okay, gamma is the strength of the non-Hermitian potential, while th is the hopping to the next side. So this is a sort of a weak non-hermitistic condition. Okay, and the in terms of the energy, energy eigenvalue is like this. So there are two energy eigenvalues actually, and let me try to tell you first how these two eigenvalues behave. So when th is greater than gamma, 2 times th is greater than gamma, these eigenvalues are both real. So they are on these real axis of the complex eigenvalue problem. So here, somewhere here and somewhere here, two eigenvalues. But when gamma equals 2 times th, then they collide at the origin, which is an exceptional point, and then split onto the imaginary axis, like this. Okay? Okay, so because of this, the transmission probability behaves like this. Okay, so because of these eigenvalues at on the real axis, they diverge. The transmission probability diverges at some point of E when the hermiticity is weak. Okay, non-hermiticity is weak, but non-hermiticity is when non-hermiticity gets stronger, then because the eigenvalue is now on imaginary axis, they have a Lorentzian peak, which is not diverging anymore. Okay, so that's how this transmission amplitude behaves. Okay, so when gamma is small, k is real, and at that point, this diverges. Okay, but when gamma is greater than 2 times th, k is actually imaginary, so it doesn't. This doesn't diverges on the real axis. Okay, that's what's happening here. Okay, so for when non-hermiticity is weak, then they diverges, which is a quite and you can see this is really large transmission coefficient, while this is still large but not diverging when non-hermiticity is uh, large. So this is actually the shape itself, that apart from the amplitude, the shape itself is a Lorentzian, which is what you see in a usual resonance. Okay, so when this also tells you in this tutorial example, you also find that when non-hermiticity is strong, it looks like a very classic resonance peak, while non-hermiticity is weak, you see a very anomalous resonance peak. Okay, and let me tell you why we have this. Okay, um, uh, so we this is again the transmission probability. When gamma is smaller than 2th, they diverge here. When does when does this divergence occur? Well, so this divergence occurs when a equals 0, right? When a equals 0, this diverges. But in this picture, what happens if a equals 0? It only has outgoing waves. Why does it can it have only outgoing waves? Well, because there is a guess or gain site, which means source potential. So particles pour out of this site, and then it spreads to the right and spreads to the left. So it pours out of the origin, and it spreads to the plus infinity and minus infinity. Okay, so that's what's happening in this particular situation. So you don't need to have an incident wave to have the transmission wave. That's why this diverges. Okay, and but when non-hermiticity becomes so strong, then the hopping, in other words, hopping is weak, then the particles that pour out of this source cannot go far away because the hopping is now weak. Okay, so they simply stay around the source and have a sort of a bound state around this source. Okay, when no hermiticity is strong. And so simply there is some scatterer here, and so you have an incident wave and transmission wave that happens. So the classic standard scattering occurs, and that's why you see this Lorentzian peak. Okay, so that's why in this particular one-side complex potential, you find this peculiar behavior for weak non-Hermitian problem. You see very sharp peak, while in strong non-Hermitian problem, you see a standard Lorentzian peak. Okay, and so this is very specific to non-Hermitian systems. Okay, now let's come back to this two-side PT-symmetric problem. And in this PT-symmetric problem, we can actually solve the problem in this way. Okay, so you have incident wave. Incident wave can have a reflection wave and transmission wave. Okay, that this transmission wave is the incident wave to this lossy potential. So then you have transmission wave, but you have reflection wave. But this reflection wave is also an incident wave on the other side to this gain potential. So you have a transmission wave and reflection wave, sort of, and so on and so on. So this is a typical Fabry-Perot resonance. Okay, you in a standard case, of course, you have real potential, two real walls, and Fabry-Perot resonance occurs when this wave bounce back and forth on between these two walls. Okay, that's actually, we'll see that actually what happens when the non-hermiticity is very strong. Okay. Now, so from this, we can find that outgoing wave on the right, on the very right, is given by incident wave, transmission here, and plane wave transmission here and going out, or this term represents this. So incident wave transmission, but reflection here at L, coming back here, and reflection from the other side, and then going out. Okay, so that's what this process means. Okay, and so on and so on. So this is an infinite series, but you can easily sum it up. And so this looks like this. And here are the results. Okay, so this is the movement of the eigenvalue, complex eigenvalues. So complex eigenvalues for uh, uh, this. Okay, so this scale means from 0 to 4 we changed the gamma. This represents the value of gamma, and this is the real axis of wave number. This is the imaginary axis of wave number. Okay, and eigenvalues move like this, okay. So it goes from the lower half, it crosses the real axis on the upper half and comes back to the real axis very slowly. Okay, because of this, for weak non-hermiticity, the resonance peak looks like this. Okay, it's strong first by on these sides, but then at some point each peak diverges like this. Okay, so here is one, and these are the divergence actually. Okay, here we change the gamma from 0 to 2, but when the non-hermiticity is stronger, then the transmission probability actually stays below 1. Okay, and eventually it's like this. This is actually the standard Fabry-Perot resonances. Okay. Okay, you remember this argument, and based on this argument, I can tell you why that kind of structure happens. Okay. Oops. Sorry. So when the non-hermiticity is weak, then what happens is here. Basically, there is a Fabry-Perot resonance. So Fabry-Perot resonance means that there are a specific wave number that resonates in here. Okay, you want a specific wave number to resonate in this between these two walls, like this. Okay, so you have a specific series of wave numbers, which is this, and this. Okay, this is actually the multiples of pi over 7 to pi over 7. Yes, because there in this particular case we had seven sites in between. Okay. Now, then, but you also has a specific wave number that for this to have a peak. Okay, you remember there is a specific wave number for this to happen. Okay, so when this specific divergence wave number falls on to this Fabry-Perot resonance wave number, then it diverges. So each Fabry-Perot resonance peak diverges one by one here, and next, when gamma is greater, here diverges here. When gamma is further greater, it diverges here. But eventually, all the divergence stops, and then finally only these Fabry resonance peaks survive, and there's no divergence anymore. Okay, so again, oops. So I think okay. So this happens also similar continuum problem. Okay, and in this case, this is the movement of the eigenvalues. Okay, so and as I when we change the gamma from 0 to 10, okay, then first this peak diverges, next this peak diverges, this peak diverges. This divergence occurs on the Fabry-Perot resonance, but which peak diverges, it's determined by this divergence condition for the source potential. Okay, so this diverging peak goes to a higher energy when you hike up gamma. Okay. Okay, so let me close my talk. As I said at the very end, we found that for weak, we found seemingly unintuitive property aspects, features of this scattering problem PT-symmetric systems. When the non-hermiticity is weak, then we find anomalous resonance peaks, while non-hermiticity is strong in the also in the first problem and the second PT problem, we found classic resonance peaks. And so that's fine. That's what we found. We argued in this paper. Okay, thank you for your attention. And let me take questions.
Thank you, Naomichi, and for your nice talk. There are a couple of questions in the chat box, but before I'm going to that, let me ask you one question, and that is also related to those. Infinite peak for low coupling, is those are spectral singularities?
This one or
Yeah, the
which one?
divergences, those divergences for weak,
Divergences?
huh? Are
Well,
those
yeah.
are those
So
the spectral singularities that,
what do you mean by spectral singularities?
yeah, in all non-Hermitian system, when this when you have collisions of complex eigenvalues, and then we can have a for bound state we can have a exceptional points, or in the scattering system we can have the spectral singularities where the transmission or deflection probabilities diverges.
So what happens is, okay, um, there are always complex eigenvalues, okay,
Mhm.
and in this particular case there are always 7 complex eigenvalues. Actually, sorry, actually on there are eigenvalues on the negative side in a symmetric way. So actually there are 14 eigenvalues, complex eigenvalues, and complex eigenvalues when we change gamma. So in this case, these are divergences. Okay. So in this sense, transmission probabilities always diverge, but mostly on the complex places. Okay. But there are specific values of gamma when each eigenvalue crosses the real axis. Okay, and we computed these transmission probability only on the real axis, real energy and real wave number. Okay, so we saw the divergences only when these eigenvalues crosses the real axis. Okay, so otherwise, we see only a non-divergent peak. Okay, is it clear to you?
Yeah. So I think in that sense, those are spectral singularities because yeah, transmission current diverges in the spectral singularity point.
Well, but they are not exceptional points.
But exceptional points are those in the bound state, right? So, but I am not sure. Yeah. So, but
No, bound states are also not exceptional points.
hmm,
So, I mean, exceptional points actually happens here.
I see.
Here.
Okay.
Yeah.
Okay.
So these are eigenvalues. Well, in some sense, they are divergences of Green's function or transmission probability. So it's a singularities, but I tend to call them simply complex eigenvalues.
So,
And
so that leads to the first question in the chat box. Somebody asked that whether you have checked that these divergence really infinite values or very large values. These peaks, when you,
when
yeah,
no, when the eigenvalues fall on the real axis, it's the true divergence.
I see.
Yeah.
May I
Well,
have
of course, in real experiments, you won't see the true divergence, of course, because there are some kind of dissipation. So you won't see any. You won't see the real divergence. But in experiments, you also should see a very large transmission coefficient. Okay.
Yeah. Other
I have a
question.
small comment.
Yeah, please.
There was last transparency where there is continuous case. And my comment is that this problem was studied by Hugh Jones 15 years ago, where he analyzed this puzzle of scattering in PT-symmetric context. It's just a comment. It was published in PhysRev
Right.
D. Two papers in PhysRev D.
Yeah. I understand that's a transparent about the transparency. Actually,
your last transparency shows the continuous limit with delta functions.
Right. Okay.
Number 26, 25.
Oh, okay. The continuum case.
Yeah.
Oh, okay. I see.
So my comment is that that this problem was studied by Hugh Jones, where he made comments on what it does mean. It was also in Hermitian conference in 2006 when he presented a talk on this problem of scattering in PT-symmetric context.
But I don't think I heard anything about the Fabry-Perot resonance.
No, it was just a scattering problem in PT-symmetric context because it was something which was open question at the time, because it was time when people started doing this optical, so to say, simulations. So it was very important point. So it's
I
nice
know, of course. Yeah. I mean, I can easily imagine people study this same problem. Actually Savannah Garmon and I also studied this system where you don't have L is 1, and we talked about various things. And so but our problem is our feature is I don't think nobody talked about this kind of features. So that's what we wanted to emphasize here.
If I may add another comment, when you return to this discrete model, so what is interesting is that you can also make this scattering unitary when you introduce proper metric in Hilbert space. But it is another story. It's just another comment that it is possible to go also to systems where the unitarity is preserved. I mean, when scattering is unitary, but you must introduce better Hilbert space. It was my papers also in 2007 where I presented a very similar example, because there were also two centers of scattering, and the balance was made in such a way that that the scattering could be unitary. But it's just a comment which is far from your subject.
Well, let me then ask you a question. So when the scattering is unitary, T plus R must be equal to 1, but
yes, that was the case.
it
Yes,
doesn't
that was the
happen
case
here.
in the model. Yes.
Yeah.
But your model
But
is
it
different.
doesn't happen here. They are not equal to 1.
Yeah,
Yes.
that's the point. That,
It's not
that if you
supposed to
make
happen
this,
also.
if
Yeah.
you made this scattering centers, so to say, different from this delta function like, so you can reach the situation in which there is really t plus r equal to 1. But because it is non-Hermitian, it is just PT-symmetric, so it is very interesting special case. It is similar to bound states. I mean, if you have bound states, they have normally complex eigenvalues in non-Hermitian case, but in special PT-symmetric cases, the eigenvalues of bound states can be real. So the same thing appears in scattering, that you may fine-tune the interactions in such a way that that scattering can be unitary. It's just a comment again because it's something else.
Yeah, well, sorry, I don't think I understood your comment, but
Yeah.
let me check your paper. Okay.
Yeah,
It goes too
let
far
me
from
interpret you. So interrupt you here. There are a couple of questions in the chat box. Federico, you want to ask your question? Please go ahead. Federico. So his question
Hi.
was that. Hello.
Hi.
Huh. So his question, let me read out his question. So one
Yeah.
question that was that these peaks are really diverging or not for the weak non-hermiticity. So that I think you have already answered. Second
Yeah.
question is that if you consider, okay, what is the physical meaning having t greater than 1? So the
Physical meaning of what?
transmission coefficient greater than 1.
Okay. So the transmission coefficient, uh, uh, so if there is no gain, or there is no source, of course, the flux must be conserved. So a squared a squared must be a square modulus must be b squared modulus and plus c square modulus. So t plus r must be 1, and so t must be less than 1. Okay, but because there is a source here, transmission wave can be greater than incident wave because the particles come out of here. So there is no conservation rule here, and that's why transmission coefficient seemingly can be greater than 1. Okay. The quick answer is the transmission wave here does not only come from this incident wave, but from the source, the particle pouring out of this here. Okay, so that's why C over A can be greater than unity.
This
I hope this answers the question.
Yeah, Hari Kumar, can you go ahead with your question?
Hi, I just wanted to know if the transmission coefficient, if it is same going from left to right and right to left, because this source and sink seems to break this.
Sorry, I don't catch your question. Maybe the first part was really too large sound, and the second part.
Yes, yeah. I wanted to find out if the transmission coefficient, if the incident wave is from the left, and if it is from the right, if they are same or like they are different. Is there any like
Oh,
theory?
if the incident was from here and here. Okay,
Yes,
so
yes.
yeah, so it's basically.
We cannot hear you. Hello.
Okay, do you hear me now?
Yeah.
Okay, so it's basically x to minus x. So and I don't remember the very. I can let me check the paper. I think it's basically the complex conjugation or whatever like that. If you make a square modulus, then and then that's it's equal. Okay. Um, let me yeah, let me tell you. So in this particular case, the transmission and reflection probability is equal. I think there can be some phase difference, but the transmission T and R from this side to this side are equal. Of course, oops. In this PT-symmetric case, it can be different because you must from this side this is source, from this side this is loss. But when you flip X and also you flip the sign of gamma, then you have the same result. So it's easy. It's quite easy to deduce the reflection and transmission from this from the opposite side. Okay.
Okay. Yeah. Thank you.
Mm-hmm.
Yeah. One last question from Jacob. Can you ask your question? Let me read out. He's asking that is there something special about the energy where the transmission coefficient diverge in the low coupling? Is there
Perhaps
something
it's
special? Okay.
so. I guess he's talking about this particular case, probably.
Yeah.
Okay, so these are determined by the Fabry-Perot wave number. Okay, so suppose you have a two walls. Then for this resonance to happen, you have to have a specific wave numbers, which is I think in this particular case is pi over 7. Okay, because we have seven sides in between. So here pi over 7, here are 2 pi over 7, 3 pi over 7, and 4 pi over 7, and that's the condition for this Fabry-Perot. That comes from the Fabry-Perot resonance. Okay, and then divergence comes from the divergence condition for this source potential. Okay, so when the divergence condition for this source potential comes exactly on to the Fabry-Perot resonance condition, then the true divergence happens for at here or here and here. Okay, I hope this answers the
I
question.
see. So the location
Okay.
of the peaks is independent of the non-hermiticity strength.
Exactly. Yes.
Okay. Thank you.
Okay, so let's thank Professor Naomichi Hatano for his excellent talk and interactions.